So now we're using data to sketch a line graph, and we've got a similar experiment. We're still using a toy car. This time the angle of the ramp is being changed and we're still measuring the stopping distance. Here is the table, stopping distances of the toy car after travelling down an inclined ramp, and the results are presented there. If you haven't learned how to use a protractor yet, a protractor is used to measure the angle of something. Units are in degrees, it's not degrees Celsius, that's temperature. But as you can see in the diagram, the angle of inclination is being changed and recorded here. So you don't need to know how a protractor works yet or how to use one just yet. Just understand that that's the instrument that we're using to measure or check that our inclined angles are recorded. So in this experiment, what is the independent variable? That is the variable that is being changed in this particular investigation. So this information is a bit of a hint that it is the angle of inclination that is being changed. So I've written that the independent variable is the angle of inclination of the ramp. If data is presented in a table, there's another clue as to what the independent variable is. We have two measurements here and we have two sets of different units, but the independent variable is always presented in the first column of a table. That gives you a clue that what is being measured there is the independent variable. It also is presented in logical order. We don't have 50 degrees up here and 10 degrees down here. It's presented in a logical increasing order. The next question we have to answer is, what is the dependent variable? That is the variable that is being measured in this investigation. Now, we've already said that the angle of inclination is the independent variable, so the other variable must be the dependent variable. But we don't want to get confused between what is measured. We are measuring both these things. Here we're measuring the angle of inclination, and here we are measuring the stopping distance of the car, just as we were in the previous experiment. But we are only measuring the angle of inclination because we want to be accurate with our experiment. Okay, we want fair testing, make sure the experiment is valid. We don't want to just lift up the ramp at any old angle and not measure it. We are only using a protractor to measure the angle to make sure that we are accurate. But the dependent variable is the stopping distance. Our next question is, what units is the dependent variable measured in? Well, again, it is still centimetres. Now, the last question, what units is the independent variable in? Well, this time we can say it's degrees. It's not degrees Celsius, that's temperature. It is just degrees. And that is a quantifiable number. That is a number that can be measured, unlike the different surfaces in the last experiment. So this gives a clue that we are needing to do a line graph. The data is quantifiable, it's a number, it can be measured, and it is continuous. It goes between 10, 20 and 60 degrees. So that is another clue. We've got continuous data, it's quantifiable, and that is a big clue that it's going to be a line graph. When we do line graphs, we are going straight to grid paper, and also your pencil again, so you could rub things out. Let's look at our scale. Remember, we need to take up most of the grid paper that we're offered. Our independent variable, that is the one that is going on the x-axis, is the angle of inclination, and that is between 10 and 60. So x-axis range is 10 to 60 degrees, and our y-axis range from the data is about, we can say it's 20 to 179, but we want nice round numbers, so we can make an axis that goes from 0 to 180, and that would cover it. So I know that a scale of, I'm only going up to 180 with the stopping distance, and I know that if I use 2 squares for every 10 centimetres, I will use a fair bit of the grid for my y-axis. And for the x-axis, I know that I'm going up by tens, so I don't have to worry too much about finding halfway between these little squares. So I'm going to choose to use 6 squares for every 10 degrees. So I've drawn my x-axis, and I've actually had to rub it out a number of times. I thought I could fit 6 little squares for every 10 degrees, but that won't fit within the grid. It ends right there. And then I had to move it back, and then I didn't really want to move it that far to the left. So I decided on 5 squares per 10 degrees. And it's just so important that, I've rubbed it out so many times, so it's so important that you do it in pencil so you can rub it out. I've put my axis label in, the angle of inclination, and I've written the word degrees. So now I've drawn the y-axis where the dependent variable is going. I've used 2 squares to every 10 centimetres. And it's really important that we start at 0. Where I've written the numbers is not halfway. Some students will write sort of in between. Don't do that, because it's really confusing as to where you are on your scale. And if you think about it, rulers are very consistently, a ruler wouldn't have the number 5 printed there, for instance. It is all consistent, and you need to be consistent on your graph too. Time to plot our data. And good thing about line graphs is we don't have to worry about gaps and things like that. We still need to be accurate. So our data says at 10 degrees, we have a stopping distance of 20 centimetres. So we come to our 10 degree angle of inclination, and we go up to the 20, which is here, and we will put across. Next is 20 degrees, and it's good that our table of data is in a logical order, so it's easy to plot as well. So at 20 degrees, we've got a stopping distance of 42. So 20 degrees on the x-axis, up to 40. Now this is 45, and that's 60. We're just a little bit under halfway to 45. So we'll put an X there. I'm plotting the last data point, which is an angle of 60 degrees and a stopping distance of 179. And a good trick is to zoom out a bit. So at 60 degrees, I might get a bit, some students sort of don't maintain their accuracy and sort of can inaccurately plot their data point. Just to make sure you don't do that, use a ruler or a straight edge on the 60. So I know that I'm going to be on this line here, and here is the 180, but the data says it's 179. So we need to be accurate and make sure that is just below the 180. Join the data points. It is continuous data, so we can do that. What I want to point out is that in maths, you might have been told when you do graphs to put arrows on the axes or extend or keep your lines going. We don't want to do that with this because it's a scientific investigation and we are after fair testing. We want to make sure that our experiment is valid. So we're not actually going to incline the ramp any more than 60 degrees because in reality, we actually wouldn't be able to do 90 because that would be straight up and down. And the car would just drop and it might not even travel anywhere. It'll just drop straight down and bounce, and that will make our experiment invalid. That is not a fair test. Similarly, we're not going to bend the ramp back below 0 degrees because the car won't go anywhere. It will just roll backwards. And that would also make the experiment invalid and not a fair test. So we don't show that on the data. We don't extend things. And finally, I've put my title in. Remember that the title has to tell you more about the context. It has to include the variables, but it also has to describe the context of what those variables are in. So we're saying it is a graph of a toy car stopping distance when ramp angle is changed.